Hello, everyone. Welcome to this webinar today. So today it is a special occasion for two reasons. First is that it's the National Mathematics Day in India, which is celebrated on the occasion of the birth anniversary of Srinivasa Ramanujan. So I wish everyone a happy National Mathematics Day and hope that you enjoy the day along with this program. And the second thing is that today is also the 25th webinar that we are doing. So it's sort of like a silver jubilee. And I'm very happy that Professor Dani agreed to deliver this webinar. Let me briefly introduce our speaker, although he needs no introduction, but I'll briefly introduce him. So Professor Dani is a very well-known mathematician. He's a distinguished professor in the Center for Excellence in Basic Sciences at present. Prior to this, he was a professor in the Indian Institute of Technology, Bombay, as well as at the Tata Institute of Fundamental Research in Mumbai. So he did his PhD from TIFR in 1975. And then he spent some time as a visitor in the Institute for Advanced Study in Princeton. He has been chairman of the National Board for Higher Mathematics and the chairman also the chairman of the Commission for Development and Exchange of the International Mathematical Union. So he has had several honors in his career, including the Santishwar Bhatnagar Prize in 1990 and an invited talk at the International Congress of Mathematicians in 1994, as well as the World Academy of Sciences Prize in 2007. So his research interests are in ergodic theory and in the history of Indian mathematics at present. And he has published over 100 research papers in reputed journals, which includes all of the top journals in mathematics, such as the Annals of Mathematics, Duke Mathematical Journal, etc. So we are very happy that Professor Dani accepted our invitation. And today he's going to speak about trigonometry in ancient India. Over to you, Professor Dani.
Right. I think there's some people waiting and that is blocking my screen. So is there some you can...
I have admitted the people. Is it okay now? We can see the cursor is moving.
Yeah. Hello, everyone. Good afternoon. And thanks to Ganit Sora for this invitation. Actually, this has been pending for quite a while now, and it's a very nice occasion they have chosen for this talk. This is the National Mathematics Day and birthday of one of the very celebrated Indian mathematicians, Srinivasa Ramanujan. Because there are, of course, many events happening, and thank you for participating in this particular one. Of course, I'm not going to talk anything really about the work of Ramanujan. I'm sure a lot of it is rather technical, which is beyond the what would be accessible to a common audience. And then about Srinivasa Ramanujan, one sort of ends up with only simple stories, etc., which is not to my liking. I mean, so, but what I'm going to speak about does have some connection, so to speak. I mean, you would have heard that Ramanujan is also known for the value of pi, which is an accurate value of pi, which is where, I mean, which is what relates to trigonometry. And in that context, maybe there is some good sense in tracing the history of trigonometry in India. That's the topic I have chosen for this occasion. Okay, so in a broad sense, trigonometry concerns the study of triangles, and then because we do it in terms of angles, it relates also to the geometry of the circle. So these are the two things which sort of intertwine in trigonometry. So here we shall review the development of developments related to this in the ancient times from India, and I have chosen to divide this in roughly the 5 themes which I have outlined here. One is understanding of triangles in the Vedic and Jaina traditions. I should tell you beforehand that this is not trigonometry in the sense that we understand it, but it still has to do with the two things about the triangles and the circles. So we might either call it pre-trigonometry or extend the idea of trigonometry to that. So, but this is something that I think is worth knowing in the context of trigonometry. The second thing will be the angle-based trigonometry in the Siddhanta tradition, which comes closer to our everyday trigonometry. Then the early trigonometric tables, that is the third theme. Then there's one interesting formula which I think needs to be a lot better known than is, and I'm going to talk about that formula, which is called Bhaskara's formula. This Bhaskara is the first Bhaskara, which is from the 7th century. Not the Bhaskara. There are two renowned, well-known Indian mathematicians from the ancient period. One is from the 7th century and the other is from the 12th century. Well, the second one is known as Bhaskara II or also Bhaskaracharya. Okay, and the last one will be the Jotpatti. This actually is about the second Bhaskara or Bhaskaracharya, and the work that followed after him. That's roughly the outline. Yeah, as I said, let's start with the Jaina tradition. Which is as far as the study of triangles or circles goes, it's more ancient in India than the Vedic tradition. So some of the compositions that we know, they go back to the 5th century. This is Chandra Prajnapti and Surya Prajnapti. However, the knowledge about these is somewhat indirect. The more direct references go to the work of the philosopher called Umaswati from about the period is not exactly known, but somewhere around 2nd, 3rd century. And his works, the Tattvarthadhigama Sutra Bhashya, that is it's a philosophical work, but all the Jaina philosophers were also engaged in mathematics. Even the founding Tirthankara, so Mahavira, was also believed to have mathematical inclinations, though we don't know much about the precise contributions. Now, unlike the Vedic people, the Jainas were motivated in their the geometry that we know from the Vedic tradition is from the sulbasutras, etc., which has to do with the yajnas and so on. Whereas the geometry from the Jaina tradition is from contemplation of the cosmos. So, and okay, so this is about the early period, and after a while, after some gap of some centuries, there are also various Jaina scholars. Some of the names you might have heard about. This is Sridhara, Veerasena, and Mahavira. Okay, and there are also Nemi Chandra and Thakura Feru, etc. These were some of the names that we will come to later. I think I might have missed saying about the order because of the little labels that I'm getting here is sort of distracting. Anyway, so this just as well. I've talked about I mentioned to begin with, I had mentioned two things: Vedic and the Jaina traditions. We talked about the Jaina traditions, but let me say also need to give some background about the Sutras. So this is the Vedic tradition. In the Vedic tradition, you know that performing yajnas was one of the primary preoccupations, in the sense it had a lot of importance. It's supposed to deliver a lot of good for you, both in spiritual as well as secular aspects and so on. And because of that, a whole lot of intellectual resources were invested in this activity. And as a part of that, geometry also developed in that period. Some of the names here, the Shulva Sutras were compositions for helping the priests to perform the yajna. So there are compositions which tell you, describe various aspects of performing yajnas, and in particular, the construction of the Vedis, the platforms and the fire altars. So they are called Vedis and Chittis. So, and among the compositions, there have been many compositions, but these four have been, have been a source of mathematical information that, as far as we are concerned. So, Baudhayana, Manava, Apastamba, and Katyayana. So, out of that, Baudhayana is the periods of these are sort of more of guesswork than any concrete evidence, but that's all we can go by. And according to that, the Baudhayana is supposed to be is believed to be from between somewhere around 800 to 500. And Katyayana is the latest. It's about 300 to 100 BC. BC is before Common Era. Yeah. So these contain elaborate descriptions of the chittis to be constructed. Maybe we'll say a little more about it later. But along the way, they also explicitly describe explicitly various geometric principles and also basic constructions. Okay, so I'm not going to go into many details of that, but a few things that from a trigonometric point of view that is contained in them is what I'm going to recall. So one of the things I think everybody should know, that the Pythagoras theorem, which is foundational to trigonometry, was known both in Shulva Sutras as well as in the Jaina traditions. People always have some vague idea that there might have been some connection of Pythagoras theorem, etc. But no, there are actually very explicit statements of Pythagoras theorem in all the four Shulva Sutras. And in the Jaina tradition, there is no explicit statement found, but some of the formulae that are described there clearly indicate that Pythagoras theorem was known to them as well. In any case, there was enough contact, I think, between the two traditions here that they would also have known the Pythagoras theorem. Now, another feature of the Shulva Sutras, as far as trigonometry is concerned, is the use of the converse of Pythagoras principle, Pythagoras theorem. What I mean here is that you know that if you have a right angle triangle, then the squares on the two sides add up to the square of the hypotenuse, right? Also, the converse is true, namely that if you have a triangle where the squares on two sides add up to the square on the third side, then that's the angle opposite to that side is actually a right angle. Now you can see that this provides a way of constructing right angles, and this turns out to be very useful, especially when you're drawing on say A4 paper, you can use a protractor or something for angles. But when you are drawing triangles on the scale that they were doing, I mean, these Vedis, etc., were of the order of 100 feet by 100 feet, etc. So on that scale, it's very useful to have a way of constructing right angles, and this serves very well. And also the specific way in which they would go about is interesting also, but I think I'll not spend time on that. And you can find it in my articles, etc. So use of converse of the Pythagorean principle to constructing producing right angle triangles is something that there is to mention, specifically mention. There was a a belief that such a thing was also done by the Egyptians, that they used the 3, 4, 5 triangle for producing right angles, but that has been doubted. There's really no evidence to that effect. Whereas in the Indian context, there is the Shiva Sutras are full of all such constructions. So, okay, in the Jaina tradition, there are a few things to mention. So there is consider a chord chord of a circle in with radius with diameter d. So let's say C is the length of the chord, A is the length of the arc. H is the arrow, meaning the segment joining the midpoint of the chord to the midpoint of the arc. Now, then there are interrelations described. There are formulae describing the interrelations of these, and well, they do it in multiple ways. I mean, there are a whole list of formulae, but many of them are equivalent to each other. But roughly, there are two basic, distinct formulas. The one is that C square equivalent to this. So they would write C in terms of H and D, etc. So C square equals 4H times D minus H, and A square equals C square plus 6H square. Now this is an exact relation. Whereas this is actually not an exact relation, but it's something that they used more as a thumb rule. And this would have been proved presumably either using similarity of triangles or the Pythagoras theorem. There are both possibilities that exist for this. And so the on the other hand, this formula here, do I have okay, this formula here, so suggests, see, for instance, when you have this chord and the corresponding minor arc, so you can think of, let's say you think of this as the chord, and so you have an arc here, and now the straight path joining this end to the midpoint of the chord, midpoint of the arc, and then to the other end of the arc. This straight path you can compute will be such that it will amount to C square plus 4H square. And to allow for the curvature, there is a bigger factor chosen here, which is 6H square. And it turns out that this is a fairly good formula. I mean, though it is apparently it would be something of chosen ad hoc, it turns out that it is quite it fares quite well. And there are also similar formulae in the Greek tradition. You must have heard of Heron of Alexandria, who faced such an issue, the relation between arc and the chord. And he gave two formulae, one improving the other, presumably. And well, which one is better term depends on the angle, but for a good set of angles, for a wide range of angles, this formula does turn out to be better than Heron's formula. Okay. Yeah, here is a description, so which I recounted. Another feature of this formula to be noted is that if you look at the particular case, when the chord is the diameter, then C will be actually D. The C will be equal to D, and H will be half of D, right? So in this, you will see that it will come to so that will actually give you, I mean, this which will correspond to the value of pi being square root of 10. Now, an interesting thing to note is that this was the value adopted for pi during those days. In fact, for a very long period until the 15th century, the value of square root of 10 for pi was very common, not only in India but also in the West. The conjecture is that it went from India to the Arabs, along with a good deal of arithmetic and astronomy, because this is related to astronomy, and that's where they got it from. And the value for as square root of 10 as an approximate value for pi was prevalent in around the world until much later, and until roughly when people started using 22/7, the Archimedean value as the approximate value. Okay. Let's now come to the later period of the Siddhanta tradition. The Siddhanta tradition means that it is in the early centuries of the Common Era, the interest developed in India in astronomy and astrology. So, I mean, many of us might consider that as the unfortunate part, but these things go hand in hand. Sometimes good things develop only along with things that are not quite desirable. But there's a development of mathematics associated with that. Okay, the early works have much in common with the Greek astronomy. So, for instance, this idea of angle is something originally from Greeks. There was astronomy in India before the Siddhanta tradition, before even before the Common Era. I mean, before Christ. So, however, that did not have the notion of angles or many other things that were not there. These came with the influence of the Greeks, especially after following the advent of Alexander the Great. And so now the Siddhanta, however, this Greek influence was sort of limited to only to a certain period. Actually, by the time of Ptolemy, who was in the 2nd century, the famous Greek astronomer Ptolemy from the 2nd century, his work doesn't seem to have influenced. It's only the earlier. Alexander, you might remember, is from the 3rd century BCE, and from then to about a century or 2 or 3 centuries, maybe there was some influence. But by the time of Ptolemy, we see that the two traditions, I mean, the Indian tradition and the Greeks seem to have developed independently. I mean, the Ptolemean tables are quite different from what are found in India and in various ways. Okay. However, the Siddhanta tradition itself was a very influential tradition in India, lasting from about the 5th to the 14th century, and also it inspired the later Kerala school of Madhava. Okay, and from the tradition, one of the important names is Aryabhata, who is considered the founder of the tradition. Though the tradition itself is somewhat older as it evolved, but his Aryabhata's work, the Aryabhatiya, was a very influential. I mean, it was inspirational to much of what followed for almost 1,000 years. Here are some major exponents of the Siddhanta tradition. Aryabhata, Varahamihira. So those who were more directly involved with mathematics or trigonometry have highlighted, whereas the other people, they were involved with astronomy and astrology, and also so in that way they did play a role, but we will not be talking more about them. So Aryabhata, then Varahamihira, Bhaskara I. Brahmagupta was a contemporary of Bhaskara I. He was on the other hand, he is actually very critical of Aryabhata in various ways. I mean, especially about the assumptions that are made in astronomy, etc. So that's and the tradition of scientific critique or even fights can go back in India on to this period. So can be traced back to that all the way as far as that. Then there are various other names, Govindaswamin, Shankaranarayana, etc. that I mentioned. This culminates in Bhaskaracharya, the Bhaskara II, was considered the pinnacle of this tradition, and in fact, very influential. And by the time, I think the whole academia had substantially changed, and there was a lot of influence of mathematics in common life. So the works of Bhaskara called the Lilavati and Bejaganita, they spread around outside just the community of people who were engaged with astronomy or preparing Panchang almanacs and so on. So, and he represents a period where he could be very influential and got a got substantial, well-deserved importance. Then there was also in the later period when one finds the work of Narayana Pandita, then Ganesha, Kamalakara, etc. These are just some of the names. I don't think we can go too much into the detail of their work on this point. Now, trigonometry, akin to what is now what we study now, appeared in India in the early centuries of CE. So, as I said, this Surya Siddhanta, which is from about the 3rd century BC, but the author is unknown. Aryabhata, on the other hand, is a very definitive thing. Of course, though for a while Aryabhata itself was not known, but now from our extant literature, Aryabhata is a very solid reference for what happened. I mean, for that period. And there's also Panchasiddhantika of Varahamira. These are some of the extant works from this period. Now, they are pursuing similar goals as the Greek trigonometry, such as determining solar and lunar planetary positions, predicting eclipses, etc. They adopted the different emphasis. Emphasis in this was different in various ways. They also, in the process of that, they were also involved in the indeterminate equations, etc. So Greek trigonometry, so one major difference when people listening to such a talk should know is that the Greek trigonometry is based on the length of chords. So when you have an angle, you can take the chord corresponding to that, or the what we actually now do in trigonometry is the half chord. Sine represents the half of the chord corresponding to half of the angle, of course. So whereas the Greek trigonometry originally, for each angle they would think of the chord opposite to that, and there are known tables of Hipparchus, and Hipparchus is also known to have produced tables. And then the Ptolemy's tables are extant, and they are well known. Hipparchus tables Hipparchus is supposed to have had tables, but we don't really have concrete. I mean, the tables by themselves. Okay, so and on the other hand, as I said already, Indian trigonometry was based on considering half chords, namely the sine as we now use. Briefly, we're having a discussion, and I briefly mentioned that the name sine is a derivative of the term ja. Ja is the term for the chord, and actually starting from the Greek chord, which was ja, they switched to ardha ja. And sometimes it was referred to ardha ja, but then for convenience, that ardha was ja dropped, and the term ja itself was used. And in this term got I mean, it is known that Indian trigonometry got transmitted to Persians and Arabs, and the course of that, there's a transformation seems to have been, and then from then on, it went to the West, first to Spain, which was conquered by the Islamic rulers, and had and from Spain, it all spread to the rest of the world. And in the course of that, there's linguistic transformations taking place, not or sometimes actually the word synonymous, the word with same two meanings was involved, and so on. And there are some theories about how the exact root, etc. But I think in view of the variations on that, I don't quite want to go into that. But it is this much is definite that the term sign that we use somehow is a derivative of ja, or more specifically ardha ja, jiva or ardha ja. So and okay, so the basic terminology is this is ja, and what we now call sign. Koti ja was the other this side is koti ja. Uh, the term cosine also somehow phonetically seems to meet with this, but that could be either coincidence or maybe chosen consciously. I don't know. And this difference of the radius and the kotija, this was also a term used. It was called utkramacha, and you'll see why later on why this is of some significance. Okay, now the sine function. We have come to the point that sine function was the thing for Indian trigonometry. Now, this was not with reference to the unit circle that we now use for our purpose, right? Now what we do when you write a sine table, you take the circle to have unit radius and angle, the half chord opposite to an angle that is called the sine of that. Whereas in Indian trigonometry, or even in the early Greek trigonometry, it was a practice to use not the unit radius, but a large radius. And what is the advantage of a large radius? It is that for various angles, the corresponding the corresponding half chord will also be a sizable number. So when you are taking unit radius, all the signs are less than 1, there'll be very small fractions, etc. Whereas when you take a large radius, the advantage is that the chord lengths that you're talking about, half chord lengths that you're talking about, are also, say, of integer size, and the fractions were a problem, posed a difficulty in various ways in dealing in the early periods. So they always prefer to have their whatever outputs or whatever they needed to list or register to be in integers. So there are various values of R that were common depending on the particular. So here I have listed some. So in the Varamira's Pancha Siddhantika uses R equal to 120. Brahmagupta used 3,270. Each one has had some rationale or some significance of that. I don't think we will go into that. The more common value for the radius was 3,438. And the point or significance of this is that when you take the radius to be this much, the circumference will be 20. I mean, you have to use a value of pi, suitable value of pi, and for Aryabhata's value of pi, for instance, it would go to 21,601. And the advantage is that this is close to, quite close to 21,600, which is 360 times 60, which is, so 300, the 360 is the number of degrees. Each degree has 60 minutes. So the number of minutes along the circle of radius 3438 will be when you have this as the radius, the circumference will be about 21,600, which is equal to the number of minutes. So therefore, for small angles, this r sine theta will be equal to the minutes. Sine theta will approximately be equal to theta, which will be equal to minutes. So this is a similar advantage that we have. So that we have in using the unit radius. And remember, the angles are measured in radians, and that's when you get sine theta approximately equal to theta. And using the radians provides the advantage that is given in that we have in using the radians is also shared by this particular choice of the radius. Okay, the sine tables were not for each degree. The early tables are not for each degree, but the quadrant was divided into 24 parts. So therefore, it would be each part will be 3.45 degrees, or about 225 minutes. So if you take the right angle, you divide it into 24 parts. I'm sorry, I not produced a should be clear what I'm talking about. The positive quadrant you divide into 24 parts, and for each part you think of the corresponding sign. More specifically, the r sign, r times sign in this. There's some talk that one why they chose 96 about the speculation, but I think I'll skip that. The real significance of 24 parts would be that while on the one hand it was adequate for applications to have that many parts, on the other hand it was feasible computationally with moderate effort to with the available tools. So for each of these 24 parts, you have to determine the values of the sine chords, and here is and we'll see how it is done. Now, what I have put up here is actually the trigonometric table from Aryabhata. So I'm going to tell you what these things stand for. So firstly, of course, it just reads, it's just one verse, one stanza, if you call. So Makhi, Bhaki, Phaki, this is a list, and these represent numbers. So this I'll not go into interpretation of all of them, but so the Makhi is 225. And if you know how the Sanskrit letters are counted, you'll recognize that Ma is the 25th letter. You start the vowel among vowels. Ma is the 25th vowel. Ka, ka, ga, 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 cha, 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 ya, etc. Go ends with pa, pa, ba, ba, ma. Ma is the 25th vowel. So Ma is assigned 25, and Kha is the second one among that. So that stands for 2, and Ki makes it 200. So 225 is this first number. Bha is, you'll now see that Bha is the 24th one. So this stands for 224. Okay, for etc. In this way, all of them are interpreted with some further. Sorry?
Sorry, sir. There was some disturbance. Sorry.
Okay. Yeah, so that is the table. Now, what do these figures represent? This tells you that the sign of the first quadrant is, which is, remember, is 225 minutes, and its R sign is just 225 minutes. Now, the second number is not telling you the sign of the second quadrant, but it is telling you the difference between that and the previous one. So the sum of the sign of the second quadrant is the sum of these two. So what it lists is the successive differences. So 224 is the first one. You add the difference of the second to first is 224. Then the next difference is 222, etc. And as you can imagine, the differences have to go down, and the last difference is just 7. Okay, that's roughly the description of the table. I'll not. Okay. Now, how there are two main methods by which these tables were computed. Firstly, one method involves that if we have a involves is having a method for sine of theta by 2 in terms of sine theta. Okay, then all 24 sine values can be computed from the known. So obviously for angle 30 degrees, 45 degrees, and also 60 degrees, you can see geometry visually what the values have to be for and from for these values there is you can you can compute them. Then these correspond to 8th, 12th, and 16th places in the table. Now, by having a formula for this, from these two, you can since you can halve them and so on, you can get the values corresponding to the first, second, third, fourth, sixth, and from just by halving and again halving whenever necessary from these values. And now you have the formula for complementation, right? They knew that they knew the Pythagoras theorem, so therefore they knew that the sine square plus cos square equals 1. So in R times the corresponding formula will hold. So correspondingly, you would know the 23rd, 22nd, 21st, 20th, and 18th term, etc. And in turn, from this we get you can now use the halving again and get fifth from here, 9th from here, 10th and 11th from term. And again by complementation of that, you can compute 19th term, 15th term, etc. All of these. This leaves just if you write them corresponding in sequence and cross out whatever is known. This leaves the 7th and 17th that remains. And now this can be found from the 14th. You already have 14. So halving and complementation enables you to in this way to compute all the terms. Now, how does one do the halving? They knew the formula for sine theta by 2, in which in our trigonometry would correspond to sine theta by 2 equal to half of square root of sine square theta by 2 plus, I mean sine square theta plus 1 minus cos square theta, which is same as half of 1 minus cos theta. And this is where the 1 minus cos theta is significant. So the sine of theta by 2 is, for that, you have to take what they call the Utkramaja, halve it and take its square root. That would be a simple formula in terms of their concepts. There's another method which corresponded to the following. A second, via a formula for the difference of successive signs. So based on the formula, so here you have delta. I have introduced the notation. Sn is the nth term of the table that you want. Then take delta n to be the difference of Sn minus Sn minus 1, the successive differences. Okay, so and now take differences of these. So if you think of replace differences by differentiation, then if you know that if you differentiate the sine function twice, again you get sine function. This is roughly what it corresponds to in finite differences. That is that if you take difference of differences and those correspond to, they remain the same. So for at each case, so this is a finite difference formula equivalent to the second order differential equation. Of course, the infinitesimals etc. were not there, but in some way they had found out, presumably by observing how the tables go, they had realized that such a formula holds, and this was sometimes used for computing these successive terms. It does not seem that this was consistently used for all the terms. So I think depending on what was more expeditious, so they used one of the two ways. And okay, yeah, as I said, so does not seem to have been adopted fully in the table of Aryabhata, for instance, as the values do not correspond to the procedure. Some are actually more accurate than one would get from here, and whereas some are according to that. Okay, apart from these, they also used interpolation, of course, for smaller. This gave only jumps of the 1/24th part. So sometimes they would be interested in signs of intermediate angles, and for that they would use, they would also involve interpolation. So signs of intermediate angles were computed using linear interpolation. So if you have an angle in between two precisely midway, then you can think of it as being adding only the half of the increment. If it is 1/3 in between, then you add 1/3 of that. So that's the idea of linear interpolation, which was also used. There's also more refined versions of interpolation used sometimes, but that came substantially later. The tables in the form of successive. Okay, some of this I have already said. A more refined interpolation taking into account the preceding term as well, and hence the rate of increase in the function. This was used by Brahmagupta in his this is a part of Khanda Kadyaka. Brahmagupta had two major works: the Brahmasputa Siddhanta, which is a more voluminous work, and he was subsequently also wrote this Khanda Kadyaka. Means Khanda is piece and Kadyaka means candy, so piece of candy. So it's an easier version of the presentation. And so as a part of that, in this work, one also finds interpolation, which sort of is not grouped in a linear interpolation, but interpolation which actually accounts for the slope at that point. So which is more naturally a more accurate one. Okay, so at the outset, I also mentioned something called Bhaskara's formula, which is intricate, and I think something that one should take home from such a talk. So an intriguing formula found in Mahabhaskara I is one of the works of Bhaskara I from around 6th century. From around 600 C. And the formula is sine theta equals r. R, of course, it has to be the proportional to the radius, and it is 4 times theta multiplied by 180 minus theta divided by 40,500 minus this is the same term without this 4. So the way it is described, this is not described in such a form that we adopt now, but that given an angle, what it says is that you subtract it from 180, multiply it by itself, multiplied by 4 here, and this term is again referred to here. You subtract it from 40,500 and make this division, and this is given as the value for sine theta. Okay, it turns out this is a rational approximation which is extremely close to the sine function over the range of values 0 to 180 degrees. The variation occurs only in the third decimal place, as one can check. Now, if you want to write it in terms of radians, what this formula corresponds to is this sine. For our sine function, it corresponds to sine theta being approximately equal to 4 times theta times pi minus theta and divided by this. Now, yeah. One thing what one might like to compare is that as theta goes to 0, sine theta by theta tends to 1. So in this case, on the right hand side actually tends to 16 by 5 pi, which is about 1.01. So this is not actually 1, but so there's a definite difference occurring as things tend to 0, but even then you see that the difference is fairly negligible. But at more general values, it turns out that if you plot something of this scale, you actually don't see any difference at all. Of course, this is purely a dramatization. I could have simply told you that they don't you can't see the difference, but by plotting such an angle sort of makes it clear that the error involved is fairly negligible. Okay, let's go over now to more refined sine tables. This come to us with the time of with the work of Bhaskara the Bhaskara II from the 12th century. More refined tables came into, and the crucial point is that Bhaskara found a formula for sine of 18. Sine of 18 degrees is something determined. This is now a part of our standard trigonometry also. Sine of theta equals 1/4 of square root of 5 minus 1, and sine of 36 equals this. So now you can use the halving method, etc., for more angles, and you can compute all multiples of 3 degrees. The same kind of arrangements that were done earlier, together with the knowledge of sine of 18 and sine of 36 degrees, you can get a sine table which extends to each multiple of sine of 3 degrees. Now, having got to sine of 3 degrees, Bhaskara also proceeded to extend it to sine of 1 degree by using this kind of formula, which is sort of inspired by how the rate of change occurs. So this is it would be determined in terms of the cos theta, sine of theta plus or minus 1 degree equals sine of theta divided by this plus or minus this. That's an approximate formula, but a good approximation in various ways. So with these, one is able to extend the table to get tables for each 1 degree angle. Okay, notice that so far nowhere did we talk of the sum and difference formulae for sine of angles, but these are have been stated for the first time in Bhaskaracharya's work. There's to the main work Siddhanta Shiromani is something called, like an appendix, which is called the Jyotpatti, that name that I mentioned in the beginning. And the Jyotpatti is devoted to various trigonometric statements, and among them, apart from the various things that I mentioned about trigonometric tables, there are also these formula sine of, well, of course, there it is again in terms of r sine, for a circle of radius r, which is 3438. This is on 438. So, but the formula is equivalent to sine of theta plus or minus phi is equal to sine of theta times cos of phi plus or minus cos of theta plus sine of phi. So there are the composition itself does not contain proofs, but and one does not know how even the conclusion was arrived at. But an interesting suggestion that has been made is that by then, in the Indian tradition, there's a lot of importance associated with studying indeterminate equations. And so looking at the solutions of indeterminate equations is likely to have suggested such a relation at an extreme. When in some heuristic limit sense, etc. That's how it is likely to have been arrived at. Okay, so from then on, there seems to have been a lot more interest in trigonometry, both for its use in astronomy as well as for its own sake. And so there is a certain curiosity about how things are they work out, and so what we might call pure mathematics in our times. And various acharyas, workers amongst after Bhaskara Acharya, there is Mahendra Suri and Kamalakara. I mean, of course, I mentioned the name of Narayana Pandita, but specifically in the context of trigonometry, these are the names that come to mind. Kamalakara, in his Siddhanta Tattva Viveka, is seen to be quite fascinated by calculations with trigonometric functions. He notes in particular the formulae equivalent to the following, and the corresponding identities for the cosine functions. So sine of 3 theta equals 3 sine theta minus 4 sine square theta, 4 sine cube theta, sine 4 theta equal to this, sine 5 theta equal to. He also notes the approximate formulae for in the reverse direction. Now, these are not worked out exactly, but the solution of cubic equations was not yet known in India at that time. But using certain approximation techniques, he also arrived at how sine of theta by 3 could be computed from sine cube theta and sine theta. So these are some of the advances. I will not go into more details, but there's one can sense the kind of fascination with the trigonometric functions that has now come in place. So I think with that, I'll thank you for your attention. Any questions?
Thank you, Professor Dani, for the very nice talk.
Thank you.
So I'd like to request the participants, if they have any questions or comments, to just unmute and ask them directly to Professor Dani. I have also got some questions in the chat. So while they think about the question, maybe I can ask one of these questions that I got from the chat. So one of these was Madhava is supposed to have had Taylor series for trigonometric functions a few hundred years before the birth of calculus. Can you mention something about this?
Yeah, I did not go into the later development. So as I mentioned, in the Siddhanta tradition inspired the Kerala school of Madhava, and so among other things, they as they were interested in the value of in computing pi, and so they did introduce various series techniques. So it's not quite the Taylor series, but the series for the arctan function, the expansion of the tan inverse function into series. This is and therefore the series for pi by 4 was developed, and this was used for computing values of pi. Similarly, Newton's sine series for sine and cosine, these were discovered by they're usually attributed to Madhava, but the sources come from the later disciples who attributed to him. So interestingly, the methods are also quite akin to calculus. So and there can be an argument that calculus originated from there, but of course that is for scholars to debate. I don't want to take sides at this point.
Thank you. So I think Vishal has a question.
Yeah.
So question. So you, while you had the slide on interpolation, you mentioned about the rate of increase, and then in the later slides also you mentioned about the rate of increase in sine and so on. And so did they have this notion of what we would say that the derivative of the sine function is cos function, and did they have this notion or this formula?
See, issue of rate can be thought of at various levels. Now, I mean, when we say the car is speeding at a certain rate, it's not that we are actually looking at the infinitesimal rate. So there is a certain sense of making a small enough division and so on. So to that extent, they certainly understood the rate of change. Whether the concept of infinitesimal rate was there or not is something debatable. There are people who argue there's something, the term tatkalika gati is mentioned in Bhaskara. So tatkalika is speed at that point. That is what it at that specific time is what it would translate to. But whether the speed was actually meant to be infinitesimal is something that is debatable. One doesn't know whether it was precisely that way. But nevertheless, in a certain heuristic sense, certainly they had the idea of what the rate of change is. And since they wrote all these tables, they would have seen that how things change. I mean the rate at which the sine function is changing is the value of the cosine function, etc. These are some of the observational things that are possible, that possibly would have been worked. And whether I mean, it's doubtful whether they would have precisely written the terms, written the rate of change in an infinitesimal way. But in terms of practice, that did not make so much difference, because the same thing got substituted in heuristic ways at each level.
So a follow-up on that question. So is there like a written evidence? Is there an evidence where they because you mentioned that they had the sine values till up to sine tables of even 1 degree differences. So did they like look at the rate of change and then say, oh, okay, this is quite close to the cosine values? Is there some written evidence of that?
Whether there is evidence, whether as to that is how they concluded, no, there is no. I don't think there can be such evidence. But I mean, there is evidence that they recognize the two as being the same. So how they recognize that one doesn't know. And conjecture is that by looking at the tables. I mean, one possible way would be by looking at the tables, and unless they had some way of deriving that. Well, of course, once the addition formulae were known, you can see. I mean, when you have specific addition formula is known, then you can see that the rate of change corresponds to the value of cos. Since the formula for this formula, when you know that when the phi is very small, and this part was known, that when for a small angle the sine value is same as the angle itself, right? That's in fact was used in the early constructions of tables. And so yeah, when this is small, this term will be phi, and this will be close to 1. So that would be from that they could make out. But it is likely that the about the change, they would have come to know even independent of that, because I think that precedes, whereas this formula itself is not very much used. Though it is stated, I don't think it is seen to be used directly, whereas the sense about rates, etc., is more prevalent.
Other sort of stupid question here. So
just one question. Did they use only fractions, or did they use any decimals also?
Sorry, I didn't catch the question.
Okay, so they have used fractions. Did they use decimals also?
Yeah, there are no decimal. There are no decimal fractions.
No decimals.
There is no decimal representation of fractions. They only used fractions in the what are called gross or whatever, vulgar fractions.
Yeah.
And that is why they usually avoided getting into fractions by choosing large radius, and sometimes they also multiplied by large factors too. For instance, if you have to find a square root of some number, which is in fraction, you first multiply it by a large number, take the square root, and then divide by the square root of the large number. That, I mean, you would have chosen properly. So not having had the idea of decimal fractions was a big disadvantage at that time.
There was a question related to this slide in the screen. So here you mentioned that there were no proofs of this sum difference formula for sine. The question was, when did such proofs appear in the Indian context?
Shadow. Yeah, okay. So just one question. I read somewhere that Aryabhata knew that eclipses are caused by shadows, but Brahmagupta apparently talked about Rahu and Ketu. Can you guess why?
No, sorry. Can you say it again?
Okay. Aryabhata knew that eclipse was caused by shadows, but
all of them knew that. All of them knew exactly how the eclipses are caused. There's no doubt about that. But sometimes, I mean, in society, there is the Puranic superstitions were prevalent. I mean, the idea that eclipses are related to two demons, Rahu and Ketu, that goes back to the Puranas. And like some of the scientists of our times also, they don't proactively contradict the superstitions. They say, okay, I mean, they try to combine merge the two. In the same way, Brahmagupta, I mean, he did his computations using precisely how, knowing precisely how eclipses are occur. But I mean, for popular display, the idea of Rahu and Ketu was also allowed to go along with that.
Okay.
So there was a question about this slide, which I got. So you mentioned that there are no proofs given of the formula displayed here. So the question was, when did such proofs appear in the Indian context?
In the first systematic proofs appear only in the Kerala works. I mean, otherwise there are some sometimes in the earlier works there are no proofs in the main work, but there have been commentators who have given some given proofs. So, for instance, in the many of the works, there is Ganesh Deva from 15th century gave many proofs for various earlier things. So, and similarly in the Kerala tradition, in Madhava's Kerala tradition, there was greater emphasis on giving proofs. But yeah, these are the two things I can mention. Ganesh Deva at a more in the principal Siddhantic tradition, whereas also in the Kerala tradition. So these are. But before that, well, uh, this does not mean that they were not proving it. It's only that it was not a practice to write all the proofs, because what must have happened is that many of the things they may have, after you discovered them and stated them, it would not be too difficult for the next person to understand why it is true. And this caught on, and until until a substantially advanced stage, it was not necessary to write proofs. It was just sufficient for all intellectual discourse to write successive statements, and people would recognize that. And then of course there is also the teacher-student relation by which you could come to understand, and this might have extended even further, even when proofs were no longer evident. I think people just were habituated not to write proofs. So that's also something that one should take into account. And besides, well, maybe the materials were also scarce and so on. Some of these arguments are also advanced, but they may or may not be quite pertinent, because sometimes one does find that people do keep elaborating on things that could be said in brief. So it's not always the economy of things that made the difference, but economy may also have played a role in wanting not to go into all details.
So I had a question, so which is probably not very related to the material, but I was just curious, like, about the tradition of mathematics in East India. Do you have any idea how it was in eastern side of India?
No, I'm afraid not. I'm sorry.
So I know that the first mathematics.
Actually, about many of these people, it's not clear the geographical location, etc., is much debated even about many people, and it's not. Aryabhata, where was he from? Whether he was from, I mean, some people argue that he was from Kerala, some people argue that it's from Patliputra, which Patna, and so on. So it's very uncertain in many ways.
So I know, for
about
example,
Bhaskara also.
So I know,
Yeah.
for example, that the first mathematics text in Assamese was around 15th, 16th century, and it was like a translation of some old work. But it is very difficult to find material, like primary sources on those kind of things, or on the person who did this. So is it a problem in all over India, or it's like some places are easier to find primary sources?
Yeah, it's, and the names of places also change, and then the similarities of names. So people have arguments about whether which place, what it represents, etc. So anyway, I can't say I have much understanding or expertise on this, so it's not. But I mean, there is an issue. There is a difficult thing to decide in many ways.
So I have one
please.
It is quite possible that some mathematics may be there, not in the math text, but in the religious text. Because the Shakti tradition, or Shaktiya, what it is called, came from East, okay? From Assam, Bengal, and so on, to the rest of the country. That is what people believe. And because that involves Sri Chakram and such things, triangles, circles, some religious texts may have this kind of material.
Yeah.
Okay. So are there any other questions or comments from the audience? If you have, please unmute and ask Professor Dani. So maybe I can end the discussion with one question. So can you recommend some sources, good sources for the study of history of Indian mathematics?
Well, some of the standard books, there's a book of Kin Plofkar, Mathematics in Ancient India, which is good. Then to study geometry in ancient India, there's a book of Saraswati Amma. Older books, I mean, the more modern perspective, I mean, from a perspective, Kim Plofker would be good. There is also a book of George Joseph, one you can read. I have some criticism of that, but about various things, but it's certainly worth having a look at.
Thank you. So maybe I can end the recording now.